Hello, this is Mr. Collier, and today we're looking at the mathematical constant e and its applications to modeling. Okay, so if e is just a constant, just like pi. It's on your calculator. It's 2.718 and so forth. It's irrational. It goes on forever. But you got it on your calculator. Just remember, it's between 2 and 3. It comes up a lot in mathematics and is very useful for modeling. Let's take a look at some examples here. Let's take a look at what the graphs of e to the power of x look like. And so here I've got e to the power of x graphed. So it looks very similar to 2 to the power of x and 3 to the power of x. It's very similar. It's just an increasing exponential function that goes through 0, 1. Okay, so it goes through 0, 1. I guess if you got it 1, then it's e, which is 2.7, which I talked about before. 2 looks like it goes up to 7.5-ish. Okay, that should have been right there. So it looks like that. Basically, it's got a horizontal asymptote, just like all exponential functions. So it looks like that. Let me label that. That's y equals e to the x. And let's do the 10 e to the x plus 2. So 10 is going to be a lot steeper. It should be plus 2. A lot steeper, and the y-intercept is going to be 12. 10 plus 2 is 12. So it goes up to 12, and it's just a lot steeper, but it still has an asymptote, horizontal asymptote, at y equals 0. So that's y equals 10 e to the x plus 2. And this one's got negative 3, so the horizontal asymptote is going to shift down 3. And it's got a negative x. That means it's going to be a decreasing function. Okay, it's got a y-intercept of negative 2. And yeah, it's got a y-intercept of negative 2. Let's use blue. It's a decreasing function. It's got a horizontal asymptote of 3, so I've got to make sure I don't go below 3 here. Negative 3. That's a little bit challenging, but it gets closer and closer to negative 3, but doesn't hit it. Okay, so I guess some comments would be, the c is horizontal asymptote, or y equals c is horizontal asymptote. That's about all you can gather from looking at these graphs. I guess you could say y equals e to the negative x, or any negative number will give you a decreasing function. Okay, anyway, they look just like normal exponential functions. And let's do some real-life examples here now. So here's f of x equals this function here. They give you the y-intercept, show that a equals 10. Well, that's just a little bit of substituting in, right? So we can substitute in 0, 13. 13 equals a e to the k times 0 plus 3. It's very nice plugging in 0 into these equations because anything to the power of 0 is 1. So we get 13 equals a plus 3, a equals 10. Given that f of 15 equals this, find k. So this is just subbing in again for the x and the y. Let's do that over here. So we're going to have 3.49 equals 10 is a. E to the k times 15 plus 3. K is up in the exponents, so let's find out k using a graph on our calculator. I think is the best way to do that. So let's do 3.49 and 10 times e to the power of 15 times x instead of k. We'll use x. So if we graph that and get the point of intersection, we can, I think the point of intersection over here somewhere. We can't see it all that well. Let's do shift plot. Okay, I don't know, 0 and 5 maybe. Actually, it might even be a negative number, I don't know. Let's see if I can see it if I change the window to this. And that is negative, it's over here. So if k is a negative number, we have a decreasing function. So, and that's, it actually makes sense in the graph here. It is a decreasing function. So we got negative 2.01 k equals negative, did I say that right? 0.201. And we got that by graphing. So to show it might work, I can just do that, negative 0.201, comma 3.49. Anyway, we got negative 0.201 for the k value. Write down an equation, the equation of the horizontal asymptote. Well, the entire equation now is f of x equals 10 e to the negative 0.201 x plus 3. And recall, the horizontal asymptote is always this one. So y equals 3 is the horizontal asymptote. Okay, let's look at another example. Perhaps this one here with bacteria, or maybe even this one here. Now let's just do this one with the bacteria. Okay, Percy Codd and Frank Finkelstein are both researchers. They are studying different colonies of bacteria. The number of bacteria in Percy's colony is given by this. So find the initial. Initial means t equals 0. So we just do p of 0. Now we can type in 0 here into our calculator, but we're going to have to graph this eventually, so let's just type it into our calculator and into apps and get all of our answers from there. 8 times e to the power of 0.3 times x. Okay, and let's do a shift plot and change this from 0. Now this is time, so I don't know, maybe 20 works well. Number of bacteria. Looks like they grow up to 350 later, so let's do 500. I don't know if that's going to work or not. Anyway, to get p of 0, we can go to num and just look at the y-intercept is 8, and that kind of makes sense. There's an 8 right here. If you plug in t equals 0, you get 8. So it is 8. Find the number of bacteria in the colony after 4 hours. That's just p of 4. And we can see that in our table is 26.6. How long does it take to reach 350? Well, we go and graph 350 here. And hopefully we can see the point of intersection on the graph, and yes, you can. So the graph is exponential increasing, and we're graphing 350. That point is going to be menu function intersection 12.6. So the answer is 12.6. Is this in minutes? Hours? Okay, next we have Fran's colony is modeled by this equation. Find k. So we have to find the k value after 4 hours. There's 35 bacteria. Okay, so that's t equals 4, f equals 35. So we're going to substitute that in. 35 equals 16 e to the power of 4k. That's probably best solved with our calculator. So let's go and type in 35 and 16 times e to the power of 4 times x. Plot. Can I see the point of intersection? Sure, it's over there. Menu function intersection. 0.196. So we got that and that. 0.196 comma 35, of course. So this means k equals 0.196. Okay. The number of bacteria first exceed. Okay. Basically, we have to find out when Percy's bacteria exceeds Fran's bacteria. So we're going to graph both of them over time. They should both be exponential, and then I'll just show what the sketch is going to look like. One's going to be more steep than the other one and overtake it. So we're basically finding this point of intersection. We've got both equations, so we can just type them in now. Okay, so this is P. This one here, function here is 8 times e to the power of 0.3 times x. The other function is 16. Oh, we practically already have it here. Hang on. Can I edit that? Oops, it's disappeared. 16 times e to the power of k is 0.196x. Okay, we got those two functions. Let's plot. We can see the point of intersection there is 6.66. So let me double check my equation. That does not match what I had before. Yeah, that equation is correct. And 16 times, yes, it is correct. Okay. That is 6.66, comma 59.08 or 59.1. So after how many hours? After 6.66 hours.